So you can't hear me in the next two clips because of how windy it was, but I'm just going to do a voice recording. So we will be talking about the Newton laws. In Newton's first law, an object in motion stays in motion, and an object at rest stays at rest, unless an outside force acts upon it. Our example is Tiki Twirl from Great America. So now we're going to talk about Newton's second law. The acceleration of an object depends on the mass of the object and the amount of force applied. For example, the flight deck from Great America.
This is Newton's third law. Newton's third law states, for every action, there's an equal and opposite reaction. Thus, two objects equaling the same net force. Our example is job zone at Great America.
Our next topic will be on force diagrams. A force diagram of a feather and an elephant as they are dropped from the edge of the building. By writing out this problem, I will be able to find the forces, draw the force diagram, and even draw the little picture, and be able to understand how the forces are affecting the object. So, object slides at a constant speed without friction. The forces are Earth and the table that the box is resting on, and these are equal but opposite forces. As you can see, this ride is going around in a circle. This is known as circular motion, and it occurs when anything moves along a circular path in a consistent way. What is going on here in this video is centripetal acceleration, because it's accelerating inward as it moves in a circle. Let's say we want to calculate the safety of this carnival ride, which means we will need to figure out how much acceleration riders would experience. Equations can help us do this, and we can use the time, position, acceleration, and velocity to calculate.
Coulomb's law states that for charged particles or objects that are small compared to the distance between them, the force between the charges varies directly as the product of the charges and inversely as the square of the distance between them. As an equation, it can be expressed as F equals K Q1 Q2 over D squared. F represents the magnitude of the force of attraction or repulsion in newtons. K is Coulomb's constant, which is 8.99 times 10 to the 9th power newtons meters squared over c squared. Q1 is the magnitude of one particle's charge in coulombs, Q2 is vice versa of Q1, and R is the distance between the particles in meters. Hooke's law states that the force needed to compress or extend a spring is directly proportional to the distance you stretch it. As an equation, Hooke's law can be represented as F equals Kx, where F is the force we apply, K is the spring constant, and X is the extension of the material, typically in meters. Hooke's law can be applied to many things in everyday life, most commonly springs because of their elasticity. For example, the spring of a retractable pen is stretched a certain distance by the force that the user applies on the pen when pushing down on the top.